Hello and welcome. Today we're going to have an introductory video about forces, what they are, how they interact, and some different aspects of them. Let's start with what is a force. A force, in its most basic definition, is simply a push or a pull. So a push or a pull. You can push on an item, you can pull on an object. And really, I've heard more complicated definitions, but that one's pretty good in terms of understanding what a force is. So let's just think of a force as a push or a pull. It is measured in newtons, named after Sir Isaac Newton. So it's measured in newtons, which are represented with a capital N. Now, the American unit for that is, or the customary unit. So the customary unit is pounds. And so when we talk about that you weigh a certain number of pounds or that you apply a certain number of pounds of force, excuse me, to an object, that is the customary unit of force. Now, what is the relationship between newtons and pounds? A newton a newton is about 1/4 of a pound. And so a baseball is about 1 Newton, a small apple is about 1 Newton. Okay, and so a Newton is about 1/4 of a pound. So 1 pound is 4.5 newtons. All right. And so that's our basic thought about what newtons are and about what forces are. There are a couple of types of forces. One is what we would call a contact force. And this is the type of force that you might have exerted on your brothers or sisters in the back seat of the car, or that you use to move a book, or that you use to move anything. These are a contact force is a force exchange through direct touch. Okay, so force exchange through direct touch. And that would be, for example, if I push on a table, if I lift a table and move it somewhere, if I pull out a chair, if I sit in the chair and the chair holds me up. All of those are contact forces because it is a force exchange where two items are directly physically touching each other. All right. Not to be confused with a field force. So type 1 is a contact force. Type 2 is what we call a field force. Okay, and a field is simply an area of influence. Okay, so a field force is where the force is exchanged or applied. Force is applied without physical contact. Okay, and that sounds really weird. People, you're like, how can you apply a force without physical contact? And in general, you can't. But there are two types that students are generally familiar with. So examples of that would be magnetic forces, because you know that if you bring two magnets near each other, they either attract to each other or repel each other, but they don't have to touch to do that. They actually attract or repel before they touch each other. And so there's a force exerted through an open space. And that's what a field force is a force applied without physical contact. It's exerted through that open space. Magnetic force is one example. And another example is everybody's favorite, gravity. And so gravity, of course, is a force between any two masses in the universe. For example, the Earth and an apple on a tree. And so the Earth is pulling on that apple, on that piece of fruit, and is pulling it down, just like it's pulling everything down. Um, and when the stem on that apple breaks, or when someone releases maybe a ball that they're holding, or a set of keys, or falls off or jumps off a diving board, anything like that, gravity then pulls that person toward, or that object toward the earth without any physical contact. There's not some giant hand that comes up out of the earth and grabs onto the apple and jerks it off the tree. That would be really, really creepy. So I'm glad that that doesn't happen. All right. So contact forces where there's direct touch, and field forces where there is not any direct touch or not any physical contact. And two popular examples that you can identify with are magnetic forces and gravitational forces. All right. Forces are a vector. Okay. So let's see. Forces are a vector. So forces are vectors, which means all the things that we previously learned about vectors. They can be represented by arrows. They can be combined head to tail. They can be moved around from one place to another to show, maybe to interpret the way that a physical situation is playing out. And so vectors can be represented by arrows, and forces are vectors, so they also can be represented by arrows. Now, let's say that we had an object, maybe a box, and maybe it's a flag, and we're going to have a tug of war. So use your imagination that this is a flag, and we're going to have a tug of war on each side. Okay, or it's a box with two ropes, whatever. And so we've got that. It's it's on a nice solid surface. Let's see. Whoops, bring it back. There we go. And so it's sitting on that surface. It's not hovering. Just use your imagination. And let's say that I have a force in one direction of, let's just say 500 newtons. And then I have a force in the other direction of 450 newtons. And let's imagine that we have these two forces, a 500 Newton to the left and a 450 Newton to the right set of forces, and they're both on this same box. Okay, how much force, first of all, which direction will the box end up going? Okay, and of course we look, and the larger force is on the left, the smaller force is on the right, and so we say, hey, it's going to end up going to the left, and you would be correct. The box is going to end up traveling that direction. But what if you, so the question is, how much force, if I combine these two, how much force would be left over to actually act in the direction of the 500 Newton force, that is to the left? And you say, well, gosh, there's 500 here, there's 450 there. There'll be a 50 Newton leftover force that will act to the left, because 450 newtons here will balance out 450 there, and the leftover will be 50 remaining that acts to the left. And you would be correct. If you wanted to represent that with positives and negatives, you could, but that sometimes gets a little confusing. So I'm going to encourage you just to represent it with arrows and put your numbers and let the arrow indicate the direction. And that will work out pretty well for you. That leftover force is called a net force. Okay. Um, a net force, or F net. F net is always the leftover. It's the part that is not balanced out by anything else. Um, and if all of my forces are in one dimension, I can take the big force, the bigger force, and subtract the smaller force. I take the bigger force and subtract the smaller force, I will get the leftover amount, which is what we call the net force. So the net force is simply the amount left over. And in this case, that is 50 newtons to the left. All right, we'll talk more about net forces as we move through the unit, but today I just wanted to introduce that idea. All right, as we continue looking at forces, let's think about another familiar force, the force of an object's weight. Weight is simply weight is simply the force of gravity pulling on an object. So if you weigh a certain amount, it's because that's how hard the Earth is pulling on you. If we went to the moon, we all know that our weight would be different. It would be less. And that's because the moon pulls with less gravitational pull because it's smaller. And so so weight is simply the pull of gravity on an object. The pull of gravity object. All right. So weight is how hard gravity is pulling on an object. It is represented by the symbol F little g, because that's well, it could be a capital G also, but I'm going to use a little g for now. And that's the force due to gravity. And that can be calculated by taking an object's mass and multiplying by the acceleration due to gravity in that local area. Okay, so if I wanted to know how much a 10 kilogram a 10 kilogram box of books weighs, I would just take that 10 kilograms of mass and multiply by 9.8 since we're here on Earth, and I would find that my weight of that box is 98 newtons. All right. So again, we can calculate the weight by taking the mass and multiplying by the acceleration due to gravity in that local area, in this case 9.8 since we're on Earth. Notice that I didn't worry about the negative, and that's because I'm just interested in the amount. If I needed to know the direction, of course, we would know that that if I had an object and I wanted to represent the force of gravity, I could just draw the arrow attached to the object and pointing downward. And then I could call that 98 newtons. And that would be a fabulous representation of the object's weight. And that would represent the pull of gravity, or the pull of the Earth, on the object. All right. Now, since I've got a force of 98 newtons pulling down, why doesn't that object just go plummeting downward? And you can see that it's because it's sitting on a surface. All right. And so that surface actually provides a balancing force that holds the object in place. And that balancing force is also going to be 98 newtons. And that's called the normal force. And that is represented by the symbol F with a capital N. Okay, lowercase n usually makes us think net, and we don't want to confuse our net force with our normal force. And so the normal force is a force, a supporting force. Let's call it a supporting force. Okay. And so we've got a supporting force. Let's see. Having trouble getting my pen back. There we go. A supporting force provided by a surface. So a supporting force provided by a surface that acts, and this is the key term here, perpendicular to that surface. Acts perpendicular to that surface. Always the normal force is perpendicular to the surface that is providing it. Um, the In this case, we've got our force that's being provided by the table or the floor, whatever that happens to be that this box is sitting on. And you'll notice that this is perpendicular to, or 90 degrees to, that surface. So whatever surface is providing that support force, it will be the perpendicular to the surface. And it is always equal to, however hard, it is equal to the force that the object is pressed against it with. Is pressed against it with. In other words, okay, gravity is pushing this box downward with 98 newtons, and that 98 newtons is all pushing into the surface, then the surface will respond back with 98 newtons. And that is how we can calculate the normal force. We'll have more examples of that as we move through the course. All right, the last thing that I want to talk about today in this introduction is something called a free body diagram. And a free body diagram, you've already seen a couple of them. A free body diagram is just a basic sketch. It's not complicated, just basic, of basic sketch of one object, only one, and all the forces acting on it. So a free body diagram is a basic sketch of one object and all the forces acting on it. For example, if I have a 5 kilogram, let's just say that I have a 5 kilogram bottle of water. So that's actually not a bottle, that's a large, well, that's about a gallon. So a 5 kilogram, it's a little larger than a gallon, 5 kilogram bottle of water. And I'm just going to represent that bottle of water with this sort of this basic shape here. All right. And let's say that it's sitting on a table. Okay, so I'm just going to draw the top of the table. And I'm going to draw the force due to gravity. and that force of gravity will be downward, and the normal force will be upward, which is the force provided by the table's surface that's balancing out gravity. Now, Fg, of course, remember, is equal to the mass times the acceleration due to gravity. That is, it's equal to the mass of 5 times the acceleration due to gravity of 9.8. And if I do the math on that real quick, anyone know what 5 times 9.8 happens to be? I believe it's exactly 49. So 49 newtons. So the force due to gravity is 49 newtons, and it turns out that the normal force is also 49 newtons. And so here I have a diagram of the bottle of water with the force of gravity on it and the normal force on it, and that is a complete free body diagram. And we'll use that to explore the forces that are acting on objects, and to be able to sort of keep track of what the results are going to be and what might be happening to them. All right, I hope all that was helpful. Hope that that gave you a good introduction to forces, and I hope that you have a nice day.